Hi class, I decided to pull up something on pH for those, just to kind of remind those what this pH is about, and really what the logarithm is about, to say more. Okay, so the pH gets born out of certain factors of algebra, logarithms. There are two logarithms in math. One is the common log and the other is the natural log. Okay, we're using the common log, log. The natural log is ln. Now, the definition of a log, common log, is a log of x to the nth power to the base 10. I don't have the base 10 down there. The log of x to the nth power to the base 10 equals n. So what a logarithm does is pull the exponent out of the clouds and put it here. If I want to go back, we take something called the antilog. The antilog. Now, what does a logarithm essentially do in this? Let's say, like in business, I have an MBA too. Let's say in business, let's say I'm in business school and I wanted to plot the gross national product over the last 70 years. Now, that would be a scroll that would go around the room if I was presenting it to the class in the old days. But if I took the logarithm, it would compress it. You would still see the increases and decreases in the G and P, but it would compress it. So that's what the logarithm does. Okay. So we go here then. Let's apply it to this. Okay. So the log is basically looking at the H plus concentration. And the H plus concentration would be like 10 to the minus 7th. And we're taking the negative log of that. So we're going to go a little further. You'll see I'm coming from. You may get confused on that part right there. All right. But the pH is the negative log of this. So you're taking the log. You're taking the exponent. Now what that means, since you're doing that, you can see that small changes in pH have a big change in H plus because you're looking at exponents, the number you're looking at. See, 10 to the 7th is a lot different than 10 to the 6th power or 10 to the 5th. So small changes here make a big difference in the amount of H pluses, which means that if you are out of range too much, you can have a problem. Okay? All right. So we go back now. I'm going to go back now. So we talked about the Henderson-Hasselbalch. We said that the Henderson-Hasselbalch was derived from this equation, and we could measure it. The arterial blood gas would provide the stuff. Okay. So we're going to go a step further. If my ideal arterial pH is 7.4, now I want you to think about it. If the ideal pH is 7.4, I'm going to make it equal. So I'm going to put 7.4 here and make it equal this. Now, that means this is set in stone, the pKa. That's a constant value that you'll have. So now I have 6.1 plus this. What does this have to equal to get to 7.4 if you already have 6.1? 1.3. Doesn't take a great genius to know that. 1.3, 6.1 plus 1.3 equals this. So then we have to say, on this part of the equation, then, like in algebra, the log base 10 of what equals 1.3? The log base 10 of what? This would be x, let's say. And that value is 20. The log of 20 equals 1.3. The log of 20 equals 1.3. Now, what does that mean then? That means that the base to acid ratio needs to be 20. The base to acid ratio needs to be a 20 to 1. The base to acid ratio needs to be a 20 to 1. That's what we have to hold it at. Now think about it. Uh, the base to acid ratio needs to be 1.3, right? If we wanted a pH of 7, what would we need? If we wanted a pH of 7, we would need another, which would be, but blood is a little more basic than water. Where are we coming from here now? Let me come back. Blood at 7.35 to 7.45 is more basic than water. See, water would be a 7 at 38 degrees centigrade. Water would be a 7, because water, and I won't get into this, but you can look at it in my PowerPoint for inorganic chemistry. Water has acid and base in it. That's really where the whole pH thing came from, was the study of water at 38 degrees centigrade. And you can easily look at that if you'd like an explanation in my inorganic chemistry PowerPoint. But the reason water is neutral is that it has as much acid as it does base. It has what? As much acid as it does base, which makes it a 7. But blood is a little more alkalotic. So what does that mean? If blood is a little more alkalotic, that means I need a little more base than I need acid. 20 to 1. Okay? So keep that in mind. I need a 20 to 1 to be perfect in the arterial blood. All right, we're going to go next to this now. Now we're getting more concepts. It's not in your book. Total acid. Total acid. That means the value that I would plug in. I'm going to this formula to make it simple. The value I would plug into here, we're going back to regular chemistry, would be total acid. Now, in the human body, there are two types of acids you have. Two types of acids. Volatile acid and fixed acid. This is an important concept. The volatile acid and fixed acid equal the total acid that would go into this formula. Total acid in the blood is measured when you calculate the pH. It makes no difference where the H plus is not prejudicial. That number, wherever it came from, it goes here. There are two acid types in the body, fixed acids and volatile acids. All right, here we go now. Work with me. There's only one type of volatile acid, and that's the acid called carbonic acid. Carbonic acid is a volatile acid. Where did they get that from? Because carbonic acid came from CO2. Now, what makes a Coke fizz? What makes a carbonated beverage fizz? CO2. So that's where the term came from. CO2 gives a volatility. CO2 gives a volatility. So therefore, the only volatile acid you have is carbonic acid. Who makes carbonic acid? That's made, you see what I'm saying? Carbonic acid has to do with that lung aspect. So carbonic acid is more associated with the lungs. CO2. All other acids in the body, every other acid you have in the body is called a fixed acid. Where did they come with that? It doesn't bubble out. See, the volatile acid, like CO2, can bubble out. That's the one, like I say, dealing with the... So all the other acids are fixed acids, like lactic acid that in muscle, hydrochloric acid in the stomach, and others. Okay? Homeostasis, if the fixed or volatile acid goes up because of a problem. See, this is where one helps the other. So if volatile acid goes up too much, because you're holding too much CO2, not breathing enough, then fixed acids go down. How would you get rid of them? Pee some of them out or neutralize them with bicarb. We're going to see in a moment. So we're just setting the stage. So I want you to keep this in mind, that when one goes up, the other goes down if we have a compensation. Remember how we did in blood pressure? If one goes up, the culprit is compensated by the helper. That's how the body works. So I want you to keep that in mind as we go through this. Here are the normal ranges again for this. See here, right here is the arterial blood gas right there. That's the normal ranges. Okay, right there. Okay. When acid-base balance in the body, in the blood goes wrong, we said it falls into 4 cubby holes as far as what it would be. And our job now is to try to figure out which of these. Now, what's the problem really with the wrong acid and base? What's the problem with pH? Denatures proteins. Remember AP1. The problem with the wrong pH is that it denatures proteins, bends them out of shape. And remember, our most important proteins are the enzymes. So we're trying to protect these proteins. Okay? So that's how that works. All right. So now what we're going to do, I'm going to start a new PowerPoint, and this is going to be pretty much the last one on this acid base. And we want to walk through how you diagnose each one of these 4. How you diagnose each one of those 4. Okay? So that's what we're going to do next. And then that should end it for acid base. Okay?